Okay, now we are gonna work on the transfer function and the block diagram of our DC machine. And just before we start, here I have the fuel voltage control and the armature voltage control. So basically is putting our flux constant or putting our terminal voltage constant and varying the other parameters and seeing what we get. So you can see with the having the flux constant and just changing the terminal voltage, we get different values of uh, TD. Our TD is our developed torque. So as we change for a given torque, we will have different responses. Okay, so this is just a quick view. Now let's start working on the model. So this is just so when we do the model, we are gonna use the flux constant and we are gonna be varying our TD because what we want is always have just one input um, because it makes things easier. So we are gonna have TD as an input. Okay, so we saw before that in steady state, or I mean in our varying time is gonna be IA RA plus LA TT of IA plus EA, and we saw that EA was equals to Ka phi omega, and we also know that our developed torque is equals to our moment of inertia times the derivative of our speed, and that our torque due to the friction is our friction coefficient times our speed, and we have our low torque. So when we have all these together, we get our developed torque, the torque that the motor is actually producing. Now, from here, if we solve for the IA dt, we're gonna get PT minus IA RA minus AA. You remember when we did the model for the induction machine, we first figured out where the derivatives were because when we integrate this, we're gonna get IA, and we need IA to calculate the other values. And the same with our torque. We know that this is equals to our developed torque minus the other ones. But for our DC machine, we also know that this is equals to K phi IA. Okay. So if we use this for these formulas and just like we did with our induction motor, we are gonna get something like this for our block diagram. So here our torques ML is equals to TL. This is written in M because this is taken from one of my teacher, well, from the teacher. He took it from a book that is in German, and in German, torque begins with M. Okay, now also you can see here we have PT as an input, we got speed as our output, and if you see here, this right here is IA. Now for constant field, we invest instead of changing our flux, we just leave it a constant. So this is they are the same diagrams, just that in this one we are showing that this is a constant. So this is always constant. So this is all the changes. Now, if we look here, what we have here, we have 1 over LA, we have BT minus RA times 1 over LA, and that is what we got here, PT minus RA minus EA, that's what we got here, over LA, and that's gonna give us the TIA. So from here we get our DT IA, and when we integrate it we get our IA. So if you look at the formulas and you look at the diagram, they are showing the same story. So here again, for example, for our developer we have IA here times our chi phi, and IA times chi phi, we get our developer. So this is our block diagram. Now, as a reminder, when we for our transfer function, when we have a system like that looks like this, plus minus, here we have G, we have our output Y, and we have another system here, H. Okay, the transfer function of this is equals to our output over our input equals to G over 1 plus G times H. Okay, so this is our transfer function. So since we only want one input, so we are gonna say that ML, because ML here is working as an input, so we're gonna say that ML is gonna be 0. So once we make this 0, this is just gonna be a line like this. So if we write a new block diagram, it's gonna be here plus minus. Here we're gonna have coming here is gonna be EA, and now these two are in parallel, so we can write them in parallel. It's gonna be 1 over RA plus 1 over LASS. So I just multiply these two because they are in series. And now we are gonna have here our K5. Remember, because we make ML 0, now we have a straight line here going to 1 over J, our moment of inertia, times S. Just multiply these two because they are in series. And we get here our omega. And down here we get our K5. And that way we get our EA. Okay. So now we can write our transfer function. That will be omega S over ptx. Remember, our output over our input equals to the top part, that is 1 over RA times K5 times 1 over JS, this over 1 plus K5 multiplying all of this. So I just follow this formula to get our transfer function. Omega S over BT X. Remember that all of this is where our LM is equals to 0. And LM is our TL. So just remember that. So this is equals to, just gonna do it step by step so you can see where all the values came from. LS times JS. So I'm multiplying this. It's gonna be equals to, well, we are adding with this. So we are gonna have here RALS times JS plus K5 square over RALS times JS. So that's the result of this. Here we can see that this one and this one we cancel, so we're gonna get K5 on top over RALS times JS plus K5 square. And this is equals to we wanted something close to it, so we're gonna try to get a +1. So I'm gonna factor out here our K5 square. So on top we have K5 over K5 square. So in the inside we're gonna have here 1 plus this RALSA and JS over K5 square. Okay. Well, we can cancel this and one of this, so on top we're just gonna have 1 over K5 multiplying 1 plus ls js over K5 square. So this is how we can get our transfer function. Okay, so now let's do this. We get this exercise that is telling us to simulate a DC machine with the following parameters. So we're gonna follow this block diagram and we are just gonna write it on MATLAB to, okay, let me open MATLAB first. Okay, so if you see here, hope you can see it. Okay, this is the diagram. So here we have our input BT. I hope, give me a second. Okay, this is a little bit better. So we have here our BT that I'm putting as an input. Here is a constant because it's a DC source, and in our script we can change the value. Now we have A here, and we have 1 over LA, 1 over S, and that's gonna give us our IA over here. And here are just using a scope and a display to show the values. Then we have our K5, and here we have our low torque. I also outed our friction torque just to show that we can get it with our friction coefficient multiplying by our speed. So basically it's the same diagram but using MATLAB, and you see gains when we have multiplying by some constant, so we can use it in our parameters later. And here for the parameters we can see the values we got for the exercise. So we have an array of 7, our inductance, our KT, moment of inertia. Now we know that for the exercise that we have done, that we have, when we have our KT in voltage over radians per second is equals to our K5. I'm just using the terminal voltage of one of the exercises, and the same for the low torque and the friction coefficient that we did for one of the exercises. So now we can just run the, well, I already run it, and we can see our speeds, our back EMF, are not correct. I hope this helps.